So slide 25. Slide 25 says, let S be a symmetric and positive definite tensor. And let the first invariant, second invariant, and third invariant of S be three principal invariants of S. Show using components that the derivative of the second invariant of S with respect to S is equal to the first invariant of S composed with the identity tensor minus S. The first thing you need to know how to do here is to know how to write this derivative in component form. So if I'm going to write this in component form, first of all, you have to remember that your second invariant is equal to half of your first invariant squared of S minus your first invariant of S squared. That must be clear, first of all, in your mind. And remember that the first invariant is your trace. Your first invariant is your trace. So if I'm going to write, I'm only writing second invariant of S now. I've not even started the question, okay? If I'm going to write this in component form, remember that what I have here is the trace of S, trace squared of S. So that's like writing alpha, alpha. You can choose any alphabet, beta, beta, minus the trace of S squared. So that will be alpha, beta, then also write the transpose, beta, alpha. So this is your first point of call, being able to write your invariant in component form. That's the starting point. Now, we now need to write the ds of this in component form. So the ds for my second invariant will be dsij, because I have to choose another alphabet for my indices for that, into half of S alpha alpha S beta beta minus S alpha beta S beta alpha. Okay. And already in your notes, you must actually know the result for this. If I have the S alpha alpha, the Sij, the answer is chronicle delta I alpha, chronicle delta J alpha. Sorry. Yes, chronicle delta I alpha, chronicle delta J alpha. It can also be alpha J. It doesn't really matter. But let me write it as it is. So look at the pattern. Look at the pattern. It means that if you are going to write the S beta beta, the Sij, that's going to be chronicle delta I beta, chronicle delta beta J. So that must be very clear to us. Look at that trend. And this is what we are going to use now to find that derivative in component form. Okay, that's what I'm going to use to write the derivative in component form. And if you look at the next one, the alpha beta, the Sij, also you know that it's conical delta, like that, like that, like that. Okay, so let's go on. And you know that in this one, you are going to have a kind of product rule. Differentiate the first one, keep the second one, keep the first one, differentiate the second one. And that is how we are going to do it until we get our results. Are we still here? Understand so far? Is it clear so far? Can you give me a quick response? I need to take off what is on the board. Okay, fantastic. I think it was Mujirade that selected this question. Okay, so let me take off what is on the board. So what we now want to write is DDSij half of S alpha alpha S beta beta minus S alpha beta S beta alpha. And we must not forget, because we've written that in component form, never forget to write your dyad. Your dyad is going to be based on, remember, what is in the curly brackets? They are all scalars. They are all scalars. The tensor that you have in this expression is Sij. Every other thing that you see is a kind of dummy subscript. Your alpha is dummy, your beta is dummy. So they are all scalars. So your basis, your dyad basis will be EIEG based on your Sij, because that is the only tensor that we have in that expression. I think, I thought it was another that suggested 26 and you suggested 25. No, another said 26, you said 25. Okay, so let's do this now. So half, just bring that half out. Let's start the differentiation. We now differentiate S alpha alpha and keep S beta beta. So that will give us conical delta I alpha, conical delta alpha J. You keep S beta beta, plus you keep S alpha alpha and differentiate your S beta beta. Because everything that we're going to get in here are going to be scalars. You can actually rearrange them, doesn't matter. But let me just keep the pattern. So I will keep S alpha alpha and differentiate S beta beta. So that will be conical delta I beta, conical delta beta J. So that would be the first one for the first term. Minus, we differentiate S alpha beta, keep beta alpha, and we do, that also. So that would be conical delta I alpha, conical delta, sorry. So conical delta I alpha and conical delta beta J, and keep S beta alpha, plus conical delta I beta, conical delta alpha J, S alpha beta. Let me write the alpha beta first so that I can continue with the pattern I'm using. Everything, don't forget your dyad. So we can perform contractions here. We can perform contractions here. You can see that on the two conical deltas of the first term, we have alpha alpha. If you do the contraction, what we just have is conical delta Ij. For the second one also, you can perform that contraction on the conical deltas. And this is what you have, S alpha alpha. So that's the first one you have, minus, perform a contraction there also on the B alpha you will see that you will have S beta I. If you do that contraction, take the alpha, okay, S beta I, and you keep beta J. Of course, you can perform a second contraction, but let's take it step by step. Minus perform a contraction again, you will see that you would have S alpha I chronicle delta alpha J. But you can perform a second contraction here for this term. This time here, if you perform a second contraction, you have S J I. For this term here, you will see you have S J I. Okay, so it means that this can be written as half chronicle delta IJ S beta beta plus chronicle delta IJ S alpha alpha minus SJI minus SJI. So we have, is the first one supposed to be SJI? Let me see. What we have there is SIJ. So let me see, what didn't I write correctly? Chronicle delta beta I, chronicle delta J alpha. Let's see. Chronicle delta I alpha, chronicle delta beta J. I think that's correct. Using the same pattern here. I think it's actually, one should be SIJ. So let me just check where I made the error. The second one, S alpha beta, chronicle delta I, chronicle delta I beta, and alpha J. That's also correct. When I perform the contraction on the first one, I have S. I hope all of you two are looking at it. Let's look at this first one and the contraction we did. If we do the contraction on S beta alpha, that should be, there's an alpha there, there's alpha here, we bring I, beta I, which is correct, chronicle delta beta J. Okay, the second contraction, alpha beta, that would be S alpha I, chronicle delta alpha J. The results I get here shouldn't be the same, because the reason is because you see the first one here, this is S beta alpha. The second one here is S alpha beta. So there's something that I did here that is causing me to get SJI, SJI instead of SIJ, SIJ. So I want to be sure that some of us have seen it. Let me check that slide 25. When we did now the SI alpha. So I'm wondering why it is written as S beta I, chronicle delta beta I, chronicle delta J alpha. No, I don't think that is what it should be. So just give me a minute. Let me just trace where this is coming from. Alpha, beta, and beta alpha should not give us SJI, SJI. This other one, okay, chronicle delta I beta, chronicle delta alpha J. Okay, that's correct. S beta I. S alpha I. Okay. We perform a second contraction. It comes to the front. Perform the contraction here also. So I'm getting the same thing here, but it shouldn't be. It shouldn't be. I'm wondering why. But anyways, if I go with what I have here, let me go with what I have because it's systematic. So that means I will have 2 SJI. And that will be EI, EJ. So if I write this back in full form, you will see that chronicle delta IJ S beta beta and chronicle delta IJ S alpha alpha is your writing like the identity tensor composed with, so this will be half into identity tensor composed with S okay? And the S that you have here, you know, S alpha alpha and S beta beta, they are the same thing. The only difference is that you use different indices, but they are dummy. So this is like saying you have two of your identity tensor composed with the first invariant of S. Remember that the first invariant of your S is the trace of S. The trace of S will give you beta beta or alpha alpha, and we have 2 of it. Then minus 2S EI EJ. Okay. Actually, what we have there should be S transpose. So I still need to look for that correction. What I should have there is actually SIJ, because SIJ EIEJ is S. SJI EIEJ is transpose of S. So the question I want to ask you is that, can you see how I move from here to here? From step this 1 here to step 2. Is it clear? From step 1 to step 2. Is it clear how I was able to go back from components to the bold form of writing our tensors? Hello, 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 everybody. No. Okay. Can I take off what is in the first part of the board just to explain that? Can I clean, because I need space so that I can be telling you what each of it is. Okay, so let me take the first part of the board off so that I can explain how we can go from the component form to the full form, because that's another skill you must know how to write. So the step 1 below that is written, what we got was half into chronicle delta IJ S beta beta plus chronicle delta IJ S alpha alpha minus 2 SJI EI EJ. What I just wrote on the board now, did we get how we got there before I go on? by performing all those contractions using the chronicle delta. Good. Now, all of us know that the trace, let's say I have a tensor S now. Okay. The first invariant of my, you know that the trace of my S is also the same as if I'm doing the trace of S composed with I. Remember that my S is Sij, Ei, Ej. When I find the trace of this, you know that this gives me Sij, Ei dot Ej. And this gives me chronicle delta Ij, Sij, which can give me Sii or Sjj. So my S alpha alpha, my S beta beta is the trace of S. And remember that the trace of a tensor is the first invariant, which is also the first invariant of S. Mojirade, is this clear? Because you are the only one that responded to me. Is this clear? So when you see S beta beta, S alpha alpha is actually the trace of S, which is the first invariant. Very good. If you understand that, then you will see that to rewrite what we have on the board to the bold form, you will see that this is the same as writing half of, you can ask, the reason why we have to use beta beta and alpha alpha is that we cannot repeat the same index 4 times. But S alpha alpha and S beta beta is the same thing, is dummy. But I could not write chronicle delta Ij S alpha alpha plus chronicle delta Ij S alpha alpha. I would have broken the index notation rule. So this is the same as saying 2 chronicle delta Ij S alpha alpha or S beta beta, anyone, minus 2 Sji, Ei, Ej. And if we are going to write in the bold form, remember there's half outside. So this is the same as saying and writing in bold form, you will see that your S alpha alpha is the first invariant of S. Your chronicle delta Ij is your identity tensor. If you remember, your identity tensor is chronicle delta Ij Ei Ej. That's your identity tensor. So if you are going to rewrite this, so this first term here is identity tensor. This second term here is the trace of your tensor S, which is the first invariant. And this third one here, remember that I was still trying to trace what it is your S. The way it appears here is actually S transpose. But I'm just, until I'm able to trace where I missed the indices, I'm just writing the answer there. But what it looks like here is actually ST. What it should actually be is S. So Mojirade, do you understand how we go from component form to the bold form now? I'm specifically calling you, okay, fantastic, good. So that answers 25. So you will see the whole step is, the question said using components, show this. But the way your self-test is moderated is that you are not going to show us the workings, but the question will be set in such a manner that you must be able to see that this is equal to this. You must be able to see that this is equal to that, okay? So let's quickly go to 26. I want to crave your indulgence. Is there a possibility of me having extra 15 minutes or 20 minutes so that we can solve some questions on grad and call and that? Can I have more minutes? Okay. So let's quickly look at 26. 26. I actually have time. If you give me 1 hour, I'll be here. But it's just that I know that you begin to get tired at some point. So I just need maybe like 20 minutes or 30 minutes so that I can still have you here. Let S be a symmetric and positive definite tensor. They gave us all the invariants, be the 3 principal invariants. Show using components. Show using components that finding the derivative of the third invariant with respect to tensor S is equal to the third invariant of S composed with the inverse of S. Like I said, the first thing is that you must know how to write this third invariant in component form. You must know how to write this third invariant in component form. And writing the third invariant in component form, this is the determinant, is the determinant of S. And I think from tensor algebra, we wrote the determinant is 1 over 3 factorial. That's 1 over 6. Your alternating symbol IJK, alternating symbol RST. Okay. Then you now have S, first index on your alternating symbol. S, second index on your alternating symbol. S, third index on your alternating symbol. So that's the pattern for you to write that. We are now supposed to find the derivative of this. Oh, and don't forget that everything that I've written here, they are scalars. Because your determinant, not everything is a scalar, but the result you get here is going to be a scalar result. So when you are finding the derivative, so here I changed to alpha beta because I've used I and J and some other things. So I can't use I and J there. Your derivative, of course, is a tensor. Your determinant is a scalar. So the derivative of a scalar with respect to a tensor is a tensor. So now let's do this in component form. Bring out your scalars from that expression. So you bring out EIJK, ERST. Then you now begin to do your differentiation. Differentiate the first one, keep the second one and the third one. Differentiate the second one, keeping the first and third like that. So that's what we are going to do. So when we do that, when we differentiate the first one, we are going to get, chronicle delta I alpha, chronicle delta R beta, SJS, SKT. That's differentiating the first one, keeping the second and the third one. Plus, keep the first one. Differentiate the second one. Differentiating the second one, we have chronicle delta J alpha, chronicle delta S beta. Then you keep the third one. Plus, you keep the first and second and differentiate the third. So differentiating the third one, we have chronicle delta K alpha, chronicle delta T beta. E alpha, A beta. Is it clear up to this point? Is it clear up to this point? First of all, write your determinants in components, then you start your differentiation step by step to get what we have. Then we now perform a contraction. We perform the contraction. So the next step, still having your scalars out, I, J, K, A, R, S, T. So we see that we have chronicle delta I alpha, chronicle delta R beta. Okay, we have nothing common there. Just hold on. I think the contraction will be performed on the, I think there's an error in what was written in the notes, but I'll get it out now. Let me check my own notes where I did mine. I was using the slides, but I've worked it out myself. So let me just get it out for us. Okay, so from what we have here, let me see, we have I alpha R beta. Okay, then I have I alpha R beta. You just give me a minute. I'm checking my own notes. Okay. So we look at the, I'm looking at the second term now. You just give me a minute. Let me quickly look at this. Okay, I've seen it. I guessed as much. There's a kind of error in what was done. So the first thing that everybody needs to note is that you can open this up one by one. That step is not in the notes. So I can write this as this 1/3. This EIJERST goes on delta I alpha R beta SJS KT. So you can actually do the contraction. So this is the first term now. Let me take this out. So what I'm doing now is this and this, opening up the brackets. So if I perform the contraction on the EIJ and the ERST, you see that this will give me E alpha JK, and the first conical delta will be off. And this will give me E beta ST. The second conical delta will be off. And what will be left is SJS SKT. Okay, so that's the first one. Now let's do the second one. EIJK ERST into SIR conical delta J alpha conical delta S beta SKT. So if we look at this closely, we'll see that we can also perform a contraction on the alternating symbols. We can also perform a contraction. And if you look carefully, you want a situation where we can actually have the same thing within the brackets and outside the bracket, noting that we still have our E alpha, E beta outside. So we can also write this as E I alpha. You see that the first conical delta will go. The first conical delta will go. Okay. So if we write ER alpha, remember we still have K here. We now have ERST, SIR, conical delta S beta, SKT. Okay. So from this point, you will see that you can actually have a contraction. There's R here and there's R on the other alternating symbol. There's S here and there's S on the other alternating symbol. So you can have E I alpha K, E R beta T. The second conical delta goes. Oh, sorry. The first term there is not a conical delta, so I shouldn't have done that. That's not where I'll do the contraction. So for the first one, this is S. I'm doing for J and alpha, that one is gone. I add E I alpha K. This is gone now once I write that. Now for the other one, this becomes E R beta T. This also goes, and this becomes SIR SKT. Okay, E alpha beta. But we also know that we can rewrite what we have here as E. I think I might need to do these steps for you and send to you. I did this long ago. I should have E alpha JK, E beta ST, and I should have SJSSKT, or the second one. So for everybody, please just pardon me. I'd worked this out before, but this step, I think I need to remember how I was able to take out the chronicle deltas. So what you can do is, class rep, after this meeting, please ensure that you remind me to send you the typed version of this question with all the steps. Is that okay? I don't want us to waste much time of me trying to trace what I did, but I remember what I did. I want to know exactly where the steps come in. Is that fine? Okay. Please remind me, this must happen today. Once it goes beyond today, I might not remember again. But what actually happened there was that the contraction made all the tensor terms the same. And the mistake in the note is that the alternating symbol is no longer EIJKERST. No, it's no longer EIJKERST. No, there are indices in that alternating symbol that changes because of the contraction. So that's where the error is. And I was able to correct that error in my own notes, but I need to perform the contraction for you. Okay, so I'll pause on that question 26. We only have 2 more steps that I need to send to you. So I'll do that after the class. Now, for the next maybe 20 or 30 minutes, I want you to choose the questions you want me to solve from slides 28 to, let's see, from slides 28 to slide 42. 2 questions from slide 28 to 42. So I'm going to mute my device now. Maybe while you are checking the questions, I can also even find the last 3 steps of this question. So 2 questions, slide 28 to 42. Post it in the chat room. Everybody, I got what happened there. So, but I want to post your question. So once I finish solving this, the last step, I got it now. I knew it was going to come to me. So let me just take this off and do the correct thing on the last step. I'm waiting for us to quickly post those questions, please, before I solve the last 3 steps here for you so that you can follow. Or should I choose any question on my own? It's like we are prepared to stay here till 1 p.m. I hope it's not a problem. As I am ready. Okay. Enola, I need 2 questions. So 29. Okay, 29 is noted. Oh, I'll do it on first come, first serve basis. So 29. Let's see what is on 29. One more question. You know that for you to be able to do 29, you need to understand what went on 28. So 28 and 29 are coupled together in a way. So we have to do those 2. But I need one more. What happened? Okay, I think you are trying to look for which one is most difficult. I'm not sure you will get it. You get it like that. Each of them has its own. It has its own thinking process behind your getting the answers. Okay, so I'm not getting any response. So we'll do 28 and 29. Then I'll pick any other question from there. Okay, 31. 31. Okay. Let me see what's in 31. Okay. So we do 28, 29, 31. Then we go to another set towards the end of the note. So everybody, are we together now? Let me just conclude this with us. Class rep, you don't need to send me anything. So what happened here was, first of all, we performed the, before we perform the contraction, we do a swap of the indices on the chronicle delta, but ensuring that we maintain the position. So the next step is EIJK, ERST. First one stays chronicle delta I alpha, chronicle delta R beta, SJS, SKT. Because everything in the curly brackets, they are all scalars, so I can change their positions. Plus, if you look carefully, you can swap. If you look at the second term there, what we want to achieve is to have SJS and SKT. Already we have SKT, but to get SJS, all you just need to do is to swap your I and J, the I on your S and the J on your chronicle delta. You won't have done any harm. Okay, so your I will go to the chronicle delta and your J will come to your S. Okay, and the second thing that you would do is to swap your R and your S. Your S will go to your tensor S and the R will come to the chronicle delta. So what this will give you is that you have SJS, chronicle delta I alpha, chronicle delta R beta, SKT. Everyone, can you see the swap of the indices? So that's just it. But just make sure that you maintain the positions where they, so if you are swapping, is the first of the first and the first. If it's second, must be the second and the second, like that. You have to maintain that. The third one, you also do, we already have SJS. So you will swap your K with your I, the K on the chronicle delta with I, and you will swap your R on the chronicle delta with your T. So what you will now have is SKT, SJS, chronicle delta I alpha, chronicle delta R beta. Please, is it clear to everybody what happens here? Are we still here? Are we still here? Are we still here? Are we still here? Good. So what will that now give us? So if we look carefully, that will now give us 1 over 3 factorial EIJK ERST, because everything inside there are scalar. So if you rearrange it, it's still the same thing. 3 chronicle delta I alpha, chronicle delta R beta, SJS, SKT. The reason why I can play around rearranging is because they are all scalars. If they are vectors, I can't try it. I can't change the positions of where all this, we are looking at vectors. We now perform the contraction now. So we perform the contraction with the alternating symbol. This becomes E alpha JK, E beta ST, 3 SJS SKT. So that's why I told you that there was an error in the notes. It shouldn't be IJK RST again. It should be alpha JK beta ST. 3 factorial is 6. 3 factorial is 6. So you have 1/6 multiplied by 3. What you have here is half. Of course, 2 is the same as 2 factorial. So this gives you E alpha JK E beta ST SJS SKT. Never forget this. Because we are in component form. This is what makes this a tensor. Without that dyad written, what we have here is they are just scalars. Okay. So I think the last, let's see what we have in the slides. Let me just go back there. That's 26. Okay. So with what we have here, you would see that if you are writing your cofactor in component form, you know, I already taught us how we write the cofactor before. I told you, you write your alternating symbols, you write your tensors. The first index of your alternating symbol, the 2 alternating symbols will go to your dyad. The second index goes to your first tensor S. The third one goes to your second tensor S, and it's half in front. So what we have here, what we have written here is actually the cofactor of S. Is the cofactor of S, which can be written also as cofactor of S alpha beta E alpha E beta. And remember that when you are writing cofactor, remember that when you are writing your cofactor, is also equal to your determinant of S composed with the transpose, the inverse of the transpose. Remember that this is the same as cofactor. But we have been told that our tensor is symmetric and positive definite. We have been told that our tensor is symmetric and positive definite. For a symmetric and positive definite tensor, the inverse of the transpose is equal to the inverse of the tensor. So because what we are looking at is positive definite, this inverse of S transpose is the same as S inverse. Because we have been told that the tensor is symmetric and is positive definite. Is this slide 26 clear now? It was Enola that chose it. Is it clear? Is it clear? Is it clear? Is it clear, everybody? So what I did that you have to know how to go back from the component form back to your bold form. Okay, good. So if that is clear, so I've resolved that, so the class rep doesn't need to contact me on that again. Let's go to slide 28. Slide 28. So please everybody note that the alternating symbol, the indices there is not correct. It's not EIJK, ERST, it's E alpha JK, E beta ST. So when you are going through it again. So slide 28, everybody. Are we ready? Should I go on? Should I go on? Should I go on? Should I go on? Hello? No. Your exam is also going to be, your exam is going to take the modality of your self-test. And you are not going to have an exam, you are not going to have an exam on chapters 1 to 3. Remember that the main continuum mechanics starts from chapter 4. So your exam is going to be the form of, because you can see that this course has a lot of things covered. I don't think there's any exam I can give you that will cover everything that you've done. But in the mode of the self-test, we can cover as much as possible. So Mojirade, I hope you got that. Your exam is going to be done like you did your self-test. The only thing is that it won't be self-test now. There will be an invigilator. If they said that the exam is going to be in 3 weeks' time, then wherever we get to. So if we get to, if we get to chapter 4, if we are able to complete the whole of chapter 4, and that's what we can do, well, that's okay. It means that your exam will have to cover chapters 1 to 4. That's what it means. I hope it's clear to everybody. So if the school says we should end there, no problem. The only advantage is that you have access to the website. So for those of you that would need some things in the course, there's chapters 5 there, there's chapter 6 there, the tutorials and the slides and everything can read up, but there's nothing I can do. You will agree with me that if the exam is going to be in 3 weeks' time, there was no way we could start continuum mechanics without covering chapters 1 to 3. So I hope this is clear, at least before we continue. Wherever we get to is what you'll be examined on, that's all. And the exam is going to be in the form of how we did the self-test. Okay, all right, let's go on. 28 now. Show that grad U dot V is equal to grad U transpose V plus grad V transpose U. Okay, so we all know that U dot V is actually UIVI in component form. So let's write this in component form. Writing this in component form, that would be UI VI, because it's a dot product, so it has the same index. Then your grad will be comma J, can be comma K, can be comma anything. But that comma J is what shows you that what we have there is a grad. And because the grad of a scalar is a vector, of course, you have your basis vector. So this is how to write your grad U dot V in component form. Now, the grad is going to be carried out because you have two scalars for your vectors there. This is the same as saying product rule, differentiate ui, keeping v, differentiate u, keeping v, plus differentiate, keep u and differentiate v. So if you use that, differentiate u, because that's the grad, keep v, and you have your ej, sorry, plus keep u and differentiate v. So it's like you are doing a differentiation and you are using your product rule to do that. Okay. Of course, you can see that this ui, j is grad u. And grad u, if you are going to write grad u, let me do this. Grad u is it a vector, tensor, or scalar? Grad u being a vector. Is grad u a scalar, vector, or tensor? Okay, Mojirade said vector. Let me see if there's any other. I'm waiting. Oh, grad u, is it a vector, scalar, or a tensor? Okay, Enola said scalar. Grad u is a tensor. Look at what we have here. U dot v is a scalar. Grad is a vector. So when you do grad with a scalar, it's just like you're having a scalar multiplication. You get a vector. Grad is a vector. U is a vector. So what you have here is actually a tensor. What you have here is a tensor. So if you are going to write this, this is written as u I, j, e I, e j. If you are going to write grad u in component form, that's what we are going to have. Please, is this clear to everybody? Is this clear? Is this clear? Is this clear? Okay, fantastic. Now, if we are going to write grad u transpose, if we are going to write grad u, everybody don't forget that this is our grad u dot v. We just wrote it out. We have not done anything to the right-hand side. We've not started working on that. All I'm just doing now is that I'm writing each, the terms on the right-hand side. I'm writing this component form. The first term on the right-hand side is grad u transpose v. So I started with grad u. I've written grad u. Grad u transpose all you just need to do is swap the basis. EJ, EI. Now, if you are going to write V, I'll have to use another index. V is VK, Now let's write grad U transpose V. So this will be written as UI, comma J, EJ, EI, VK, EK. And this can be written as UI, comma J, VK into EJ, EI, EK. Are we following, please? Are we following? Are we following? Are we following? Is it clear up to this point? So I'm checking that when I write grad U transpose V in component form, I get the first term here. Good. Now, when a dyad operates on a vector, we've done that before. This will give us UI, comma J, UK, EJ, EI dot EK. And that, oh, sorry, that's VK. VK. And that gives us UI, comma J, VK, EJ, chronicle delta IK. And when we do a contraction, this is the same as saying UI, comma J, VI, EJ. So you will see that this is equal to this, and this is this. Remember that we got the expression in the box by just carrying out that differential using product rule. So we've gotten the first term. Now let's write grad V transpose U in component form and see whether it's equal to the second term of the component form we have. Can I go ahead or give you a minute, maybe for those that are trying to write? Should I go on? Uh-oh. Where's everybody? I want to believe that everybody is still hearing me. Okay, I should wait. Okay, good. I purposely broke this down in steps so that you can see it. So let me wait. Okay, so I'm going on now. So let's write the second part. So let me just take this off. I know some people might still be looking at Enola. That's from chapter 1. Chapter 1, when you have two vectors, the dyad product operating on a vector is the same as this. We have seen that from chapter 1, long time ago. And we're also able to prove it using component form. So Enola, you will need to go back to chapter 1. This we've done long time ago. Is something that by now we should know. I hope that's clear. Chapter 1 is a building block for 2. 1 and 2 is a building block for chapter 3. So let's do so let's write grad V transpose U. Or is that grad V? Yeah. Grad V, transpose of grad V, U. So let's do that. So first of all, if you write your grad V, in component form, that's VI, J, EI, EG. So it's like we are following on from what we did before. So if you just go through the same step, I don't think I even needed to do this. Just swap. And if you have your U also and you write it as UK, EK. So it just follows on from the same thing that we did. Just follow the same steps and you will see that you will get the second. So what you have will be grad V, U, then you have your EJ, EJI on your EK, and you have chronicle delta IK, and from there you have VI, J, and there's EJ left here, J, UI, EJ. Because these are scalars, you can rearrange it like it was rearranged here, and you'll be able to see the proof. So we'll go to 29. I'll just give you a minute to just should I go on? I want to be able to do 29 and 31. It's not easy talking for 3 hours, so I think I am already running out of steam. Okay, so 29. We are supposed to show again that grad U dot V is equal to grad U V plus grad V U plus U cross call of U call of V plus V cross call of U. All right. So the first thing is that we should know how to write the two, everything that is written here, we should know how to write it. For example, grad U, we already had the expression for grad U dot B previously. So you can use the previous thing that we had to get the expression for this. But we want to be sure that everything on the right-hand side also gives us the same results like we have on slide 28. So the practice here is how to write from this form to component form. So grad U, right now, everybody should know how to write that. U, I, comma, J, E, I, E, J. That's grad U. Now, if we put our V as V, K, E, K, it means that grad UV will be U, I, comma, J. If you do the VK, if you go through the steps that we did before anyways, I wanted to skip it, but this will be VK, EI, EJ, and this will be EK. And of course, this will give us chronicle delta JK. So this gives us UI, J, VK, EI, chronicle delta JK. And when you perform that contraction, you get your grad UV to be UI, comma, J, VJ, EI. So that's the first term. The second term, just based on what we've written, we all see that grad V U, just put V where U is, U where V is, to be V I, comma, J, UJ, EI. Of course, which you can write, if you want to write your U first, use the same as UJ, VI, comma, J, EI. The next thing is to write our U cross col V. So first of all, we must know how to write col V. Col V, already, we know that our col V is written as, is like the trace of, if you go to your notes, there's a part of the note that tells you how to write a call. I think it's call V want to write, not call U. So everyone, you must be able to know that writing call V is EIJK, alternating symbol, VK, comma, J, EI. So just look at the pattern. The first index on the alternating symbol is on your basis. The call of a vector is a vector, okay? The call of a vector is a vector. So you will see that your first index there is on your basis. Then you write your K before your J on the, it's like you are doing, your VKJ is like a grad, then you are doing a trace somewhere there. Just check your notes, you will see, but this is how to write call V. Now we want to do U cross call V. Because I've used I, J, and K, just to be sure that I am not breaking any rule, I'm going to use M in this case for U. So UM, EM, I'm doing the cross of that with EIJK, VK, comma, J, EI. So remember that your cross product goes on your vectors. Your UM is a scalar. Your alternating symbol is a scalar. your VKJ, they are all scalars. So what you actually have here is UM, or let me write the EIJK first. EIJK, I can rearrange that because they are all scalars. UM, VK, comma J. Then I have EM cross EI. And when you are performing a cross product, you know you get your alternating symbol, and for this particular case, you get your alternating symbol with your basis. You get your alternating symbol with your basis. So in this case, EMEI will give you alternating symbol MINEM. Okay, so that's what we are going to have. That's this cross product here, gives you this MIN, then the last index I brought in on that alternating symbol, this should be N, sorry. This should be N. Is it clear so far? I'm breaking this into steps. You can see that these steps are not there, just to show you. And I might not be using exactly the same indices. It doesn't really matter. They can use alpha there, I can use M here and all that. The steps I've done so far, is it clear? What I've done, I wrote call V. I know what U is. I'm now doing the cross product, okay? So if I rewrite that, so what I will have here will be EIJK UM VK, J EMIN EN. That's what I will have. So I can bring the alternating symbols together, and that will give me EIJK. I can rewrite the other alternating symbol as EINM. So far, I'm going in the same direction so that I don't have a negative. So I'll go counterclockwise. So I can write this also, is the same thing I'm writing, EINM. Then UM VK, J. This is J, EN. I'm still doing U cross call V. That's all I'm doing for now. Okay. So I know that there's a relationship between the alternating symbol and can be broken into real product of two alternating symbols. You can break them down into conical deltas. I want to take off what is on the board right now and move to, okay, let me take off the first part. So what we'll have now, we use the conical delta alternating symbol relationship. We have conical delta JN, conical delta KM minus conical delta JM, conical delta KN, and everything into VUM UM VK, J En. Okay, so what does that give us? So in the first place, if you open up that bracket, you see that the conical deltas, of course, will act on your other scalars there. So this with this, you will get, first of all, you perform your contraction. So instead you have UK, conical delta Km goes, VK, comma J, then EJ, the second conical delta goes, minus UJ, the first conical delta goes, okay? The first conical delta goes. So we have UJ, okay, KJ, EK. Okay, so let's compare with what we have. Let's see whether our patterns are the same. So if we go to the slide, we have UK, VKJ, EJ. Then the second one, UJ, VKJ, EK. So that's correct. So this is our expression for U cross call V. Systematically, you just work your way using all your rules. Okay. And of course, we know that this can also be written as, so what was just done here was a little bit of manipulation. So for it to be clear to us, I'm sure some steps were skipped. I don't want to do that. So we already know that for us to get this kind of results from the first thing that we did, you will see that this is the same as saying, if you look at the next thing that is written there, you see that this is the same as your grad. Look at your first note. This is the same, the first thing I underlined here is same as your transpose of your grad VU. In the first slide, we had grad U transpose. But you know that when you transpose your grad, what you did was that you swapped your bases. So I want us to check this result, compare it with what we have in the previous slide. If you tell me you are not able to see it, it means I have to work it out for you. Can you actually see that what we have first here is transpose of grad V on U? Check the result for grad V transpose U and see whether you can see this. I'll give you a minute. I'm looking at time and I still want us to do 31, so I don't want to do this out again. Look at the index on your K and J and EJ, and look at the one that you have for grad V transpose. Can you see the difference between, okay, seen, Enola has seen it. Every other person, I need one more person, then I can move on. And you will see that this other one that is here is actually grad V U. So if you look at the two, you see that one, for the first one, the first index K is the first index on your V. If you look at the second one, your first index J is your second index on your V. So one is a transpose grad of the other. Then if you look at your basis vector, you see that we have VKJEJ. The second one, we have VKJEK. So you will see that for your grad, when you transpose, you see that the second index on your V is your basis. It's actually supposed to be the first index. Please, I need you to check and you can confirm that this is actually this. And all you need to look at is the position of your basis, the index on your basis vectors, and where the position of the index of those basis vectors sits on your V. You will see that one is a transpose of the other. And of course, you know that your V call, so this is equal to U call V. So for your V call U, just put your U where your V is and your V. So this will be grad U V minus grad UV. So if you take everything that we have written now, there are 4 terms there. Grad U on V, grad V on U, plus U cross call V, and V cross call U. You should get the same. If you take all those things together, you should get the same results that we had in this. So what we actually have here is going to be taking everything together. You see that what we have is grad U V plus grad V U plus grad transpose of that grad V U minus grad V U plus grad transpose of that grad U minus grad U V. So this goes, this goes, and what you are left with, transpose of grad VU plus transpose of grad U V, which is the same thing that we had on slide 28. So 31, as the last question we are going to deal with. From what we've done, I think 31 will be a form of walkover, but it's okay. 31 is easier than what we just did right now, so it won't take us time. Steps: ensure you can write the component form of all that you have written. Check the left and the right hand side and see that the result you're supposed to get is what you get. So that's just it. And once you write in component form, be able to return back to the bold form, to the tensor form. Can we do 31 so that we can close? Can we do 31? Hello? Or we should close the meeting? Okay. So let's do 31. So 31 says, show that grad U cross V is equal to vector cross grad V minus this vector cross grad U. Like I said, know how to write it in component form and check the two sides. Of course, we all know that U cross V is the same as writing EIJK UIVJEK. Or it can be whatever form. What I wrote here and what is on the in the note is the same thing, because you know that EIJK is the same as EJKI and so on and so forth. Now, if you are going to write the grad of that, so just put everything here in so that's the grad. And don't forget, this will give, remember U cross V is a vector. So the grad of a vector is a tensor. And your diode will be EK, EL. Based on the indices that I am using. There's a missing, the EI, if you check the slide, the EI is missing in the in what was written here. So, oh yeah, it has to be, the EK needs to come out, is one of the diodes. That's correct. So that EK is what came out to give us the second basis for our diode. So this is the EK here, then the EL comes from this comma L here. All right, so if we open this up like we do, and you do as if you are doing the differentiation using product rule, your EIJK is a scalar. So the L will not act on it. So we have EIJK. Differentiate your U, keep your V. UI, L, VJ. Put your diode. Plus the alternating symbol. Keep your U. Differentiate your V. VJ, L, EK, EL. And remember that when you are writing your vector cross, remember how we write our vector cross. For example, if I have, let me not use U or V. If I have A cross, how do I write it? It's a tensor. So if I put E, let me use MNP so that it won't confuse you what you are doing. That'll be AN So I want everybody to check that when you are writing a vector cross, this is how it's written. Just check your notes and quickly say, yes, it is correct. Anyone checking? Because the next step, that's all that you need to know. You already know how to write your grad V. You already know how to write your grad V, and you already know how to write your grad U. So if you look at the first thing here, already here, you will see that you have here a grad U. There's a grad U here. Whatever it is that you have here should take care of your vector cross. How the vector cross is written. And if you look closely here, you see that what you have here is a grad V. Okay. And whatever is written here, you will see that in a way, you are going to have a change of sign on your vector cross. So that's why I'm saying, can anyone confirm that when we are writing this kind of vector cross, this is the way it's written? And we are taking so much time to respond. I think we don't hear from anybody. I'll just tell you to go look at it. So you will see that I know you are here. I'm saying confirm what is in the rectangle. Is that how to write a vector cross in component form? I just need you to say, yes, I'm correct. Or no, I'm not. Or maybe I mistakenly, the way I put the indices is not correct. So I'm waiting for you to check. Because by now we should know how to write the vector cross. It's, I think we did this in tensor algebra. What do you mean I've not reached that place? I don't understand. Vector cross is tensor algebra. I didn't understand what Akiode said. It's correct. Okay, Enola, thank you. If it's correct. So if this is correct, if I'm going to compose this with a grad, for example, if I'm composing it maybe with a grad B, okay, if I'm going to write grad B, this is the way I'll write grad B. I'll write grad B as maybe B, let me use something else, BR, comma S, and because grad B is a tensor, I'll have this dyad. So I want to use this for you to check what we have to be sure that what is there is correct. So if I now do A cross grad B, so what I will have will be EMNP. I will have AN. I will have BR, comma S. Then I will now have two dyads. And you remember the rule for when you have products of dyads. You keep the first basis, the second basis, the ones inside will become chronicle delta. They will become a dot product. So this becomes EMNP AN BR, comma S, chronicle delta PR EM ES. And because of this chronicle delta, you can perform a contraction such that what you have is EMNP AN BP, comma S EMES. Once you get what I did here, all you just need to do is to track here and track this to see that what you have will be a U cross grad V minus V cross grad U. That's all. So all you need to do is, how do they write vector cross? How do they write the grad? When you put it together, what do you get? Then begin to look at the placement of the indices to see what it is. Like in this case, because I don't have space, this should be EMNP. Or let me create space here so I can compare. Let me write this again. So this will be EMNP AN BR, S, conical delta PR EM ES. And when I perform that contraction, I will have EMNP AN BP, S EM ES. So just look at the placement. Look at what we have at the top. We have U, we have UI, L. Here we have BP, S. You will see that the L on your U is on the basis, is the second basis, which is the second basis here. Okay, which is the second basis here. Then you will now see that your M, which is the first here, your M is actually the M is actually the I that we have here. The M is K, sorry, your M is K, and the M is the first. So you know that this can also, if you write it the other way, to be K, KJI, you have a negative there, okay? So if you track the two of them, you see that the one that has the V cross will give you a negative, and the one that has the U cross will give you a positive. So you see that the second one here will be the positive one. This one will be a negative because if you see the placement, look at your VJ. Okay, here we have AN, which is your VJ here. The EIJK, N is in the middle, I is my M, okay? K is supposed to be in the other placement. So it's as if you have rewritten the EIJK in a form that it becomes negative. So you need to compare this, the placement of the indices, and compare this. And you will see that one of them, the alternating symbol will give you a negative. And that is why in this case, you have a negative here. The V cross here is going to be a negative because it doesn't follow the order. So please check this and you will see that we have the same results. So you have to learn how to write your vector cross with your grad of your vector. I will need to call it a day now. I'm no longer as sharp as when we started the class because I've been speaking for 3 hours, 15 minutes. So that's a long time of speaking. So you will see that that's why I have to quickly show you an example of how you do this last one because I've run out of steam. I think what I can do is 3 minutes, any questions? For those of you that have written this, out, I would expect that you would have quickly checked that what we have at the top there is a U cross grad V minus V cross grad U using that, okay? So apologies, I cannot go further than this. I won't be up to now. So we have to stop here. The self-test for chapter 3 we open today, and it will close on Tuesday evening. It will close on next week, Tuesday evening. So let's get that done. So when they say we're having an exam in 3 weeks' time, did they give us the dates? Do we have a date? Everybody, please give me date so that I can see what I can predict for us how our exams will look like. No date for now. I don't really understand. If they say it's in 3 weeks' time, there should be dates now. I always like to plan my. Okay, let me see our course package before we go. So I can tell us where we would end this course. Continuum mechanics, let's see. I actually had to give you an extra week. By now, we should have actually started kinematics, but you asked me to give you some time on the chapter 3, so that's why we are behind. So if I check our first day course package, by this week, today is 8th, you will see that this week we're supposed to have started kinematics. If they say exam will be in 3 weeks, it means that we have till maybe end of June, if that is correct. So there might be a possibility of us covering chapters 4 and 5. There might be a possibility. If not, I think we'll just stay on chapter 4 and see where it goes. Yeah, 3 lecturers can be done actually. There's 3 lecturers done. Are you doing self-test with the 3 lecturers? Are you reading notes with the 3 lecturers? Are you doing tutorial sessions? And are you taking self-tests? Actually. So I don't think that we can compare the modalities. We actually had a scheme that covers how many weeks now? We had a scheme that covers 14 weeks, and 14 weeks is actually the number of weeks for a semester. But because lectures were supposed to start in February, if I'm correct, we didn't start until April in the department. So what it means is that we don't have the number of weeks that we are supposed to have for the semester, as in if we look at the start dates for the course. I don't know if everybody can get what I'm saying. So our first day course package was arranged based on the number of weeks for a semester. Yeah, so it's not my fault. So what it means is that we are going to take off maybe 2 weeks because we are the ones that didn't start early or thereabout. Anyways, I think everybody is clear. I'll be in class physically. I should have been in class on Monday, but Monday is a public holiday. Am I correct? So we should have actually Monday and Wednesday. But because Monday is a public holiday, I can only come on Wednesday. So we'll do chapter 4. Let's see how far we go. Cover chapter 4, do a tutorials. If that's where we stop, it means that we'll see in exams. But I'm hoping we can do chapters 4 and 5. All right, thank you, everybody. Yes, continuum mechanics is not wide. It's just because we've not done tensor, algebra, and calculus. Tensor, algebra, and calculus shouldn't be part of. Continuum mechanics actually starts from chapter 4. But we spent a larger part of the semester trying to, because if you don't know chapters 1 to 3, you won't even be able to read the material for chapter 4 and 5. So the course actually is in 2 parts, vector and tensor, algebra and calculus. Then the second part is continuum mechanics. But we are doing a 2-in-1. Anyways, thank you, everybody. All the best in your self-tests. I'm looking forward to seeing everybody's face, at least putting a face to all the names that are here when we see next week. All right. So bye-bye, everybody. Bye-bye.